Today we're going to discuss normal subgroups. Let's do a review from the last lesson. Remember that a subgroup is a non-empty set H, which is also a group. Simply put, H is non-empty and is closed under products and inverses. If we do have a subgroup, we'll write this less than or equal to symbol, H less than or equal to G. Last time we talked about a simple way of determining whenever a non-empty subset is indeed a subgroup. The following three statements are equivalent. First, H is closed under products and inverses, that is, H is a subgroup. Second, H circle Y inverse is an element of H for all X and Y in H, that is, H is closed under quotients. And third, the pair H along with our binary operation circle is a group. In order to get an idea of how to define a normal subgroup, we have to introduce homomorphisms between two groups. To this end, let's let G, along with the binary operation star, and H, along with the binary operation diamond, be two groups with identities 1 sub G and 1 sub H, respectively. First, we say that a well-defined map from G to H is a group homomorphism if it preserves the binary operations. What we mean is that the image of X star Y is phi of H diamond phi of Y for all X and Y in G. There's a certain subset of the codomain H that we care about. This is called the image of phi. It's a set of elements lowercase h and capital H that look like they come from some lowercase g and capital G. That is, lowercase h equals phi of lowercase g for some g. And finally, we define the kernel as a certain subset of the domain. That is, the kernel consists of those elements lowercase g that map to the identity in H. That is, phi of lowercase g is 1 sub H. Well, these two subsets are actually pretty interesting to study. If we have a group homomorphism, phi, from G to H, then first of all, if I take any element G and raise it to a power, say n, then phi of G to the n is simply phi of G raised to the n power. You can use this statement that you prove inductively to show that phi of G is a subgroup of phi, the kernel of phi is a subgroup, and that the image of phi is also a subgroup. Let's let phi be a group homomorphism still. For any element A in our codomain H, we define the inverse image of A as the set of lowercase g such that phi of G is A. We can write this as phi inverse of A, again the inverse image, or we can write this as X sub A. We'll call this the fiber of phi over A. This is a subset of our group G. We'll denote G bar as simply the collection of such fibers. That is, as we let A range over the codomain H, we'll consider the collection of all X sub A. We'll call this the collection of fibers of phi. Soon, we'll try to turn this collection of fibers into a group itself. Let's let G, along with the binary operation star, and H, along with the binary operation diamond, be two groups. And let's denote capital K as the kernel of a group homomorphism from G to H. We have four statements. First, we can always write each fiber X sub A as a left coset and a right coset. That is, let's pick an element G that lies in the fiber over A. That is, phi of G equals A. Then we can express each fiber as little g star k, which is also equal to the right coset k star little g. Remember that here k is the kernel of the group homomorphism. Second, G bar forms a partition of G. That is, we can write G as a union over the fibers X sub A, where the fibers themselves are disjoint. That is, there is no intersection between them. Third, we have a binary operation on the fibers of G. That is, if we consider elements x sub a and x sub b, where of course a and b are different elements from our codomain capital H, we can define the operation by simply looking at what happens with the fibers. So for example, xa circle xb is x a diamond b. Again, this allows us to take any two fibers and quote unquote multiply them together. With all of this, the fibers now under this binary operation forms a group. We'll use this now to give a definition. This set G bar is called a quotient group or a factor group. We will write G mod K as G slash K as this quotient group. Let's let H now be any subgroup of G. We'll consider the sets G star H, this is a left coset, and H star G, this is a right coset, as our coset representatives. Again, remember that here H is any subgroup. It's not going to be the kernel of a group homomorphism in general. Since G bar is a partition for G, we have a coset decomposition. That is, I can write G as the union over these fibers, where we union over certain elements A coming from our codomain H. And remember that we can either write this in terms of left cosets or right cosets. As long as K here is the kernel of a group homomorphism, both the left cosets and right cosets are equal. Let's give an example of all of this. Let's let G be the integers under addition, and let H be a cyclic group of a finite order n. Let's consider the following map. We'll send an integer m to x raised to the m power. You can easily check that this is a group homomorphism, because the image of a sum of powers, r and s, will simply be the product of x to the r times x to the s. Because x to the m is e, precisely when the order n divides m, we see that the kernel of this map is simply the collection of multiples of n. We can write this compactly as n times the integers z. The image of this map is the entire cyclic group, so phi here is actually a surjective map. With this in mind, we can actually consider now the fibers over any element xa that come from the codomain H. Here we're considering the set of integers m, such that x to the m is x to the a. Again, we want the set of integers such that phi of m equals x to the a. When we stare at this, and again remember that x to any power is the identity, as long as that power is divisible by our order n, then we see that the fiber simply looks like multiples of n that have been shifted by a remainder a. That is, we can write it in the form n times z plus a. Now remember that our cyclic group consists of simply n powers of x, namely 1, x, x squared, so on and so forth, all the way up through x to the n minus 1. Since there are n fibers corresponding to these x to the a's, as a ranges from 0, 1 through n minus 1, then we see that really what we're doing here with the fibers xa is we're considering the remainders after dividing by n. Again, these remainders will be these powers a equals 0, 1, so on and so forth through n minus 1. So the fibers actually keep track of the remainders after dividing by n. We'll consider these fibers to be elements of our quotient group, namely z mod nz, where we'll consider an element in z mod nz to be this class here, nz plus a, this fiber. Remember that we can identify the elements of this quotient group, namely z mod nz, as the same as elements of the cyclic group. That is, we'll take the fiber nz plus a and identify that with the power x to the a. We're now in a position to finally define normal subgroups. Let's write down a general result. Let's let G be a group. Now we're changing our notation. Instead of star as the binary operation, let's consider circle as a binary operation. And let's let K be a subgroup of G. Then the following four statements are equivalent. First, there exists a group homomorphism, phi, such that K is the kernel of phi. Second, left and right cosets are equal for all elements little g of capital G. That is, little g circle K equals K circle little g. Third, the normalizer of K and G is actually equal to G. That is, n of K equals G. And fourth, G circle capital K circle G inverse is contained in the kernel capital K for all elements little g of capital G. Again, these four statements are all equivalent. So any subgroup K satisfying either of these equivalent statements is said to be a normal subgroup. In this case, instead of saying that K is less than G, we'll put a little arrow next to the less than to make it look like a triangle. And we'll say that K is normal in G. Let's give an example. Let G be a group. One example we can write down is the so-called commutator subgroup. Here, we consider all possible commutators from G. As we range over elements lowercase g and lowercase h, we can write down the commutator, bracket g comma h, and we can consider now the set of all such commutators, and let g raised to the c power, the commutator subgroup, be the smallest group containing all of the commutators of G. In this case, one actually proves that this commutator subgroup is a normal subgroup of G. Let's give an even more specific example by looking at G being the dihedral group of order 2n. In this case, you can actually consider various commutators, and what you actually realize is that the commutator has to be generated by even powers of R. R remembers the rotation. Therefore, we see that the commutator subgroup is the group generated by R squared. This is a cyclic subgroup, and the cyclic subgroup either has order n or it has order n over 2, depending upon whether n is odd or even, respectively. As another example, let's consider the center of our group G. Any subgroup H contained in the center is automatically normal. In particular, the center itself is a normal subgroup of G. And here's our last example. Let's say that N and K are two normal subgroups of G. We can consider the intersection of these two, which we'll call the meet. We've seen before that the intersection is a subgroup of G. In fact, you can actually prove that the intersection of two normal subgroups is also a normal subgroup of G. Similarly, we can consider the union of these two normal subgroups. We've seen before that the union in general is not a subgroup of G, but we can consider the smallest group containing N and K, containing the two of them together, and that is now a subgroup generated by N and K. We call this subgroup the join of N and K. Not only is this a subgroup of G, but it is also a normal subgroup of G whenever N and K are normal. Thanks for watching.